Hello students. Till now in the RISC-V ISA study, whatever we have seen are the arithmetic and logic instructions that are available in RISC-V, and following that we looked at the data transfer instructions also, namely the load and store instructions, right? And we also understood why we would require the load instructions and store instructions. Basically, it's the requirement imposed by the load store architecture, right? We can't have everything in the registers, so we need to go to the memory. So the to and fro would happen only through the load and store instructions. Now in this lecture we are going to look at another set or another class of instructions that have a totally different purpose. Now all the instructions we have seen so far, the ALU and the load store instructions are uh, once they get executed, the hardware will go to the immediately following instruction. Means it would we would call that as a sequential instruction. Let's say I'm executing an add, uh, and let's say we have a sequence of 5 add instructions. So once the hardware executes the first add instruction, it's going to move to the second add instruction, right? Once that gets executed, we move on to 3, then 4 and 5. That's how we proceed. We call that as a sequential execution, right? Whatever instructions we have seen so far will not um, affect the way hardware would execute these instructions, right? By default we'll go sequentially. Now what if we want the hardware to execute a code which looks something like this, where there is a possibility of more than one path. So let's label them as path 1 and 2, and the path which we pick is based on some condition. Here the condition is whether I and j are equal or not. If they are equal, we will take path 1 and execute the instructions in path 1 and then go on to exit. If I is not equal to j, then we will pick path 2, execute all the instructions in path 2 and then go to the exit, right? When we say execute, we have to instruct the hardware to execute either path 1 or path 2 based on the outcome of this condition, right? This point where we do a condition check, and based on the outcome of this condition where we have we pick one of the two paths, it's called branching, right? The paths can be more than two also. We are going to look at that case in a short while. So this instruction should enable the hardware to branch or to either path 1 or path 2 based on the outcome. What do we mean by picking path 1 or path 2? If you remember, a program counter, PC in short, will be pointing to the next instruction that we expect the hardware to execute, right? In the previous example where we had 5 add instructions lined up, when we are executing the first add instruction, PC would be pointing to the second add instruction. That's the reason after the first instruction is executed, we use this PC, take the second instruction from the memory uh, and execute it, right? But now we need a provision where the PC need not be always the next instruction. It can be anywhere else. So this kind of provision is given by what's called as control instructions. We will now look at those instructions which will help the hardware to make the decisions, and based on the decisions it will pick the appropriate path. The conditional operations, we call them, right? The comparison, greater than, less than, etc. They all come under the branch instructions. What we expect the branch instruction to do is, if the condition is met, we expect it to go to a labeled instruction. Now what does a label mean? You can say it is an alias for the instruction, means another common name that we give for our convenience at the assembly program, right? We are going to see how that gets eventually converted also into the machine code, but for now just we'll go with the point that if the condition true is true, then we want to branch to some labeled instruction, but if the condition is false, then we'll go to the next sequential instruction. So just to give you a more relatable example, let's say we have an instruction with label I1. This is the actual instruction which is making the condition check and will help us to pick one of the two paths. So the next sequential instruction, which is I2, uh, can be anything in one of the paths. Following that, we have another sequential instruction, so on. So this can be the path 1 that we saw earlier, right? Then eventually somewhere down the lane, we can have an instruction I20, then I21, etc. These would belong to the second path. Now what we expect the hardware to do is once it starts executing I1, it will do the condition check and it will pick the next PC appropriately. Means the PC will be either I2 or I20 based on the outcome of this condition check. Okay, now let's look at what all condition checks that RISC-V allows us to do. The very first one is the equality check, right? The instruction is called branch if equal instruction, and its mnemonic is BEQ, branch if equal. It has two register operands and an label. Here that label is L1. You can put it as anything else. In this example, you can put it as I20, for example. What happens, or at the hardware, what happens with it when this instruction is getting executed is the value in RS1 is checked with the value in RS2. If they are equal, it will branch to the instruction which has label L1. Excuse me. If they are not equal, then it will continue the execution of the next sequential instruction, which is I2. Excuse me. The other equality or inequality check, you can say, is branch if not equal. In short, it's B and E. Again, it has two register operands, and following that we have a label. So similar to BEQ, here what is done is the value in RS1 is compared with RS2. If they are not equal, then PC will be equal to the address of instruction with label L1. Otherwise, PC will be equal to the address of the instruction which is just following this BEQ. The next sequential instruction, we call it. Okay. Now let's go back to the previous example that we saw where we wanted to compare two values I and j, and based on the outcome of this comparison we wanted to perform either an addition of g and h or subtraction g minus h and assign it to f. The C code would look something like this. It's a simple if else statement. If I equals to j, then f would be in f equals to g plus h, else f equals to g minus h. Right? When do we go to the else? Only when I is not equal to j. It's a pretty straightforward thing that most of you are already used to now. Right? It's a simple if else statement. Now let's see how this gets translated into the RISC-V assembly code. Let's assume that the values of f, g, h, I, j are available in registers x19, 20, 21, 22 and 23. The RISC-V code would look something like this, which any standard compiler would have generated. The very first instruction is B and E, we are comparing the value of x22 and x23, which is I and j. If they are not equal, then we are saying that jump to an instruction which has label 1. So the instruction with label 1 is here, which is subtract. What are we subtracting is g and h, and the resultant is given to x19, which is f. After that, we have, let's say, the common path, which is labeled as exit. Now, if the value in x22 and x23 are equal, then obviously we do not branch to label 1, but instead we go to the next sequential instruction, which is add x19, x20 and x21. So what we do here is we sum g and h and write it into x19, and after that we are including another additional branch instruction, which is beq x0 x0 exit. What this does basically is it compares the value in x0, which is always 0, and it jumps to exit. It means that we are always taking this branch. Why we have included this additional branch is, consider the case where the third instruction beq is not there. What happens then is, if we have not taken this branch, we execute the add instruction, and immediately we also execute the subtract, which is false. Sorry, which is logically incorrect, because we want either addition or subtraction to be performed. So to avoid the subtraction, we have introduced another label exit, which is just after the path 2, we can say, right? This is the common path for both path 1 and path 2. Now, typically in the compiler, when it's analyzing the program, it will introduce these labels into the assembly code. And the assembler, when it's generating the machine code, will replace these labels with the appropriate addresses. Now we are going to see how that's done also. So during the assembly process, assembling of this particular piece of code, label 1 would be replaced with the address of this subtract instruction. The exit would be replaced with the address of some other common path instruction, right? And then the same logic can be achieved in many other ways. So I'll leave it to you to explore. Here what we have shown is that we are doing comparison of I not equal to j, but you can do the same thing with I equals to j. So the code will change a little, so that you can take it as a practice and explore. You'll better understand how the control would be moving. Excuse me. So the BQ x0 x0 exit, right? We have a pseudo instruction also. I'm going to speak about the pseudo instructions a little later, but in the RISC-V, there are some pseudo instructions which are not standard instructions. That again, the compiler is not binded to handle these pseudo instructions. Okay, they are not the standard RISC-V. They are just for convenience. So for BEQ x0 x0, we have a pseudo instruction. You can check that in the RISC-V reference datasheet that I gave you. Now, how do these control instructions or the conditional operations affect? Is they change the execution flow of the instructions. Instead of always going sequentially, we either go to the sequential instruction or we can go to some other place. That's the basic functionality of these control instructions. Now, how do we do it? We already saw that we change the program counter. The program counter is the address of the next instruction that we want to execute. And if we set the program counter to the next sequential instruction, then that's the path we want to take. Otherwise, we can assign it to the address of the labeled instruction. And this would be done by looking at the outcome of any condition that we have put. So what we have seen so far is equal to check or not equal to check, right? So in addition, we also have uh, the common case kind of a scenario where we might sometime need to compare a value or a variable with 0. So we have some pseudo instructions for it. Branch if not equal to 0 is a pseudo instruction, and beqz is the mnemonic for it. And branch if not equal to 0, the mnemonic is bne. So it has one register operand and the target label. So basically what this pseudo instruction is, it is something like this: beq x5 x0 and target label. So we are comparing the value in x5 with x0. That's what we want here. Branch if equal to 0. Same thing here. Branch if not equal to 0. So these beqz and bnez are not supported in the Venus simulator that you are using now. Okay. The operations that we have seen so far are equal to, not equal to, and we saw some uh, branch if equal to 0, branch if not equal to 0 kind of pseudo instructions. What other conditional checks that Lec5 supports is branch if less than. It would look something like this. BLT is its mnemonic. We have two register operands, RS1 and RS2, and we have the label. Here it's L1. So what this instruction does is the value in RS1 is compared with RS2. If it is less than, then we jump to L1 or we branch to L1. Otherwise, the instruction that's immediately following BLT is executed. The other conditional instruction that Lec5 gives is branch if greater than or equal to, right? So its mnemonic is BGE. Again, just like the other branch instructions, we have two register operands and the target label. Here, the value in RS1 is compared with RS2. If it is greater than or equal to, then we are going to jump to the instruction with label L1. Otherwise, we are going to execute the next sequential instruction. Here is an example that I want you to try out. So try to generate the Lec5 code for this particular if statement. If A is greater than B, we want to increment A. Otherwise, we just want to fall through. Give it a try, and if you face any difficulty, we can discuss during the tutorial or the live session. In the branch instructions, just like a few of the arithmetic instructions had the unsigned variant, we have the signed and unsigned conditional checks. So what we have seen is branch if less than, branch if greater than equal to. These are signed comparisons. It means the values in RS1 and RS2 will be treated as signed numbers. But there is an unsigned counterpart also, which is BLTU, BGEU. Branch if less than unsigned, branch if greater than or equal to unsigned. What these instructions will do is the value in RS1 and RS2 would be treated as unsigned values and the comparison is made. So an example can be something like this. Let's say x22 has the value which is all ones, and x23 has these are the bit positions, all zeros, just the LSB position is 1. So if we want to do a signed comparison, the way these values are interpreted is x22 is interpreted as -1 and x23 is interpreted as +1. So x22 is less than x23 will be yes. But if we want to compare as unsigned, then the value in x22 is a very big number and x23 is just 1, right? So here x22 is greater than x23. So the branch instructions that you want to introduce into your code, right, be careful with them whether you want the variables to be treated as signed or unsigned. Now let's look at how these control instructions are encoded. There is a specific format, SB format for this, and it looks something like this. It has opcode function 3, which is 3 bits. Then we have the two register operands rs1 and rs2, each taking 5 bits because we have 32 registers. And following that, we have what's called as the immediate field. Basically, it is the distance of the target address or the target instruction, right, where we want to jump to. Now, what do we mean by distance? Is the address of this branch instruction, and whatever, whether we want to, or let's say we want to jump to somewhere below. In the previous example, let's say the very first example we took, instruction 1 was a branch, and then we had instruction 20, right? So the difference of these addresses, right, I20 minus I1 would be the immediate value. And just as a reminder, each instruction in RISC-V is treated as a 32-bit value, right? So accordingly, the branch instruction and the target will be so many bytes apart. So that value is encoded in the immediate field. So the LSB 1, 2, 3, 4 bits positions are here, then 5 to 10 are here, the 11th bit is here, and 12th bit is here. Now you can ask why such a scrambled mess, right, instead of giving a 12 bit space here. Right, there are two things. One, we do not want to change the positions of rs1 and rs2. It points to the regularity design choice. The other is the hardware designers have suggested such an encoding because it simplifies their decoding process that we are going to look at in the next module. Okay, so the immediate value that we introduce in this machine code will be added to the PC to get the actual target address. So this is called PC relative addressing. Now you can correlate it with the load store instructions where we had the base register to which we had added the index, right? So here the index would be the immediate value and the base register is the program counter itself. Mostly the way we write programs, we see that the branches are very nearby. Now the branch target can be nearby. The target can be before the branch instruction or after the branch instruction, right? We want to go back to some previous line of code, or we want to jump further down. So accordingly, what we have something called as forward branch and backward branch. If the immediate value is positive, it means that we would jump to some instruction further down the lane. So it's called forward branch. If the immediate value is negative, then it implies that we want to jump to some instruction which is somewhere before this branch instruction. So it's called a backward branch. Now at the hardware, to execute this instruction, the processor would need to regenerate the target address using this immediate field. Like I said, it would use the PC. So the target address would be the current PC plus the immediate value given in the machine code times 2. Now here are a couple of questions that I want to think you to brainstorm about and come up with the reasons. Why did we omit immediate 0, right? We said that immediate field is 12 bits, and we are saying that bit positions 12 to 1 are stored, but it's usually is 11 to 0. But why did we omit immediate 0 here? And accordingly, you'll also find an answer on why we are multiplying it with 2 here at the hardware. So I'll leave it to you, brainstorm, and if it's still not clear, we can discuss either in the live sessions or Piazza. Now what we have seen so far is the simple if and else. Now how to deal with the switch statement? Switch is used whenever we want to select one of many possible alternatives based on some particular condition check, right? So the very straightforward way would be the naive way that we would have learned right at the beginning of our programming, is just convert the switch into a sequence of or a chain of if else statements, right? Accordingly you can generate the assembly code also. But can we do any better? There is one very interesting and intuitive way on how we can optimize this piece of code at the assembly. The idea is, let us store all the target addresses, means the addresses of all the alternatives uh, into a table. Let's call that table as branch address table or simply branch table. Now based on the condition, a condition checks outcome, we will index into this table. And when we index into this table, what do we get is the address of that particular case. So each alternative of the switch can be viewed as an entry into that branch table. So you will have a practice question in your next lab. Try it out, and if you are not able to figure it out, right, we can discuss on that. Let's extend the further. We have these control instructions that we saw, which are branch if equal, branch if not equal, branch if less than, branch if greater than or equal to. Now let's say we want to realize a while loop, which is something like this. We have an array I, a array of I value. We are comparing it with some constant k, and if it matches, as long as it matches, we want to increment I, right? So let's assume that the values, the variables I, k are available in x22 and x24, and the base address of the array is available in x25. The compiled RISC-V code would look something like this. So here my loop is the label I have given to this particular instruction, and the same label I have used here. So here the very first instruction is shift left logical immediate. The immediate value that we are giving is 3, and what we are shifting left is the value in x22, which is I. Basically, if you remember the array indices, how we are calculating at the assembly that we had a discussion on a couple of lectures back, we need to generate the index. We have the base address in x25. Now we need to generate the index so that, sorry, we need to generate the offset so that they can be added and we get that particular element. So the offset is being generated here, and that is added to the base register x25. So now in x10 we have the address of array of I data. Now using that address, we are using the load double instruction to put it in x9, and we use that and we compare it with x24, which is the value of k. If it is not equal, then we are exiting the loop, but if it is equal, then the value in x21 is incremented by 1, which is I uh, plus statement here, and we want to go back to the loop, go back to the beginning of the loop. So that's what we have done here, beq x0 x0 my loop. So when this particular instruction is executed, we go back to this loop, and the same thing would repeat. Now here I have put a question why we are shifting it left by 3. The assumption I made was this array is handling 64-bit numbers. If it were handling 32-bit numbers, then this value would be 2. And instead of load double, we would have used load word itself here. So it depends on what kind of data you want to store in this array. So accordingly you would generate the RISC-V code. In Venus, because we can only handle 32-bit numbers, so you would be writing LW, and here you would require to be uh, introducing only 2, not 3. So with that, I will pause this lecture. What we have seen in this lecture are some branch instructions, and what all branch instructions are there, the signed, unsigned version, using those branch instructions, how can we realize if else. Then I left a discussion point on how we can realize a switch statement. You will, like I mentioned, you will have a assignment question on that, work it out. And following that, we also had an example on how we can realize a simple while loop. In the practice assignment, you will also have opportunity to realize a do while loop and for loop also at the assembly. You once you practice that, you will realize how close or how different the assembly code would look for a while, do while, and for loops. I want you to go through that process to see in case there is any difference or not, right? With that, I will pause this lecture. All the contents of this lecture are in section 2.7 of the textbook. With that, thank you.